Hello, and welcome to application session 1 of this Introduction to Linear Algebra with Wolfram U. The topic for the session is polynomial interpolation. So let's begin with a brief overview of the session. So here is a pair of points which I've called data. The first point is 1, 3, next one is 3, 7, and so you might guess that the polynomial 2x plus 1 passes through these points. So here is a plot which shows that you have the linear polynomial over here and the 2 points over there, the 2 data points over there. Now, this linear polynomial can be used to interpolate the values for point between the two given points. So you could take a point over here, for example, like 2.3, and work out the value over there based on the interpolating polynomial. So this is a simple example of an interpolating polynomial. So here's a more formal discussion. So let's say given n points in the plane, then there's a polynomial degree at most n minus 1, could be less than in some cases, which passes through these n points. And this polynomial is called an interpolating polynomial for the given set of points. Let's say you have 3 points, then you have polynomial degree 2, etc. Now, the main point is that this polynomial can be constructed by solving a system of linear equations. So although you have a nonlinear problem, you actually have a linear problem sitting below it. That's the solving of a system of linear equations. And fortunately, we have a very nice function called interpolating polynomial, which can be used to compute this polynomial. So I'll take a few examples of actually solving the system, and then we'll use the built-in function straight away. Okay, so as a first example, here is again a set of 2 points. I want to construct a linear interpolating polynomial. So I call it p of x equal to ax plus b. The problem is to determine a and b. So I'm going to set up a linear system for a and b. And what I do is I set up the equations over here. So basically, I evaluate the polynomial at the x values and set them equal to the y values. Okay, once I've done that, I can solve the system for a and b. I can plug in the solution, and so I have that the polynomial is 2x minus 1, which looks correct from here. So let's plot the polynomial in the data, and you see that you actually have the correct fit over here. So on to the case of a quadratic interpolating polynomial. So now I've got 3 points, 3 data points. So I'm going to have a quadratic function fitting them. I set up an equation system with 3 unknowns. So for a, b, and c, 3 equations, 3 unknowns. I solve the system, plug it back, obtain the polynomial, and when I plot over here, then again, there's a very nice fit. Okay, so now the next case would be a cubic interpolating polynomial. So now I've got 4 data points, but this time I'm going to use the built-in function interpolating polynomial to get the answer. Now the point is this: in so-called Horner form, it must be expanded to get a nice answer from a day-to-day perspective. So that's the expanded form. And again, if you plot over here, you see you get a very nice plot of the data points and the interpolating polynomial. Okay, so as the first simple application over here, let's say I want to construct a quartic polynomial, degree 4, with these roots over here. So I set up a data set with 5 points. The first 4 points are just the roots over here, so 2, 0, 7, 0, 5, 0, negative 3, 0. And the last one is more or less arbitrary, but I just pick it so that I get a nice polynomial. So here's the interpolating polynomial, and clearly that's going to pass through the required points. And then I can plot over here, and you see that you have roots exactly at those points, and this is the value at the 5th point. Okay, a second application, I have the sine function. Now, the sine function is surely not a polynomial function, but there's some data for it. So I construct an interpolating polynomial. It looks a bit messy, so I can use the chop function, which chops off very small parts to get a slightly more elegant expression. I can plot the data points and the polynomial over here, and it looks like the fit is quite nice. So if I try to compute the value at pi over 4, it looks like the approximate and the exact values are quite close to each other. But now if I go further away, you see that actually the approximation gets quite poor. So the main point is that interpolation is good where it is valid, namely between the point, but once you stray away from them, you might get a pretty bad approximation. So one has to be careful when doing interpolation and using them for applications. Okay, so that's the end of this session, and the main point is that an interpolating polynomial of degree n minus 1 can be constructed for any set of n points in the plane, and this polynomial of course passes through those points, and it can be used to interpolate the values between the points. Now, for us, from the linear algebra perspective, you actually would solve a linear system of equations to get the coefficients for that polynomial. And of course, we have a built-in function, interpolating polynomial, which can be used to compute this polynomial for large sets of data, keeping in mind that as the data sets become large, the computation will become quite complicated. So I'll stop over here. Thank you very much.